Hello class, so this is CSE 5250, section 1, week 3 of spring 2023. So here I have instructions for your first programming assignment. So this is going to have you uh, write a few programs that I've showed you in the last video. So basically, I showed you how you can work with OpenMP. Now it's your turn to try it out for yourselves. So, the first one is pretty simple. Write a multi-threaded hello world program. Run the program with as many threads your computer will allow. If your computer is, for example, an 8-core, 16-thread CPU, then you should expect to see 16 hello world messages. Keep that number in mind because you're going to need that for part 2. So for this part, you're going to submit the source code, a screenshot of the program running, and for part 1, you're going to want to also experiment with changing the amount of threads you have. So you're going to want a screenshot of the program running with a different thread count. So again, if your program initially produces 16 threads, you can set that thread count to, in theory, anything you want. Part 2 is to write a parallel for loop using the example of dot product of two vectors. Now this is the example that required declaring a critical section. So, yeah. If in part 1 you determine that your program will by default create 16 threads, try to have at least 16 threads, 16 elements in your vectors. Or if you have a 4-core CPU that's 2 threads each, so 8 threads, you'll want your vectors to be at least 8 elements in size. For this part, you want to submit your source code and a screenshot of the program running. You can use last week's material to help you out with this. Again, this is going to be a walkthrough of what we can do, and then later on I'll start talking about more of the theory, and then we're gonna pick up from there and look at the sieve itself. I've put the sieve on the back burner, but eventually we'll have to come back. We'll circle it back to that. Okay, so that's your first assignment. One of your next assignments is actually going to be matrix multiplication. So, when we last met in class in person, I alluded to the idea that you can conceptualize matrix multiplication as a series of dot products. So, let me pull up a visualization for that. Give me a second. So first time I'm just gonna draw a pair of matrices. So where's the pen? Yeah, there it is. Okay, so I'm just gonna demonstrate this with square matrices because that's easier to conceptualize for our purposes. Okay, so we have matrix A here and matrix B here. If you want to find the product of these two matrices, since these are 2 by 2, the answer is going to be 2 by 2 also. We can generalize this to any size matrices that we want, but let's stick with the square cases because that's easier to conceptualize. So, what would be the product of these two matrices? What is A times B? Well, we can start off by calculating one of the elements. Since this is going to be 2 by 2, this first element, I'll just cut to the chase. It's going to be the dot product of this row vector and this column vector. Let's call this C0 and C1. This is its own column vector. And this is going to be its own row vector that we're going to call R1, so this is R0. So this first element, so this first thing here is going to be the dot product of R0 and C0. Likewise, this is going to be R0, dot product of R0 and C1, then R1 1.C0, and finally R1.C1. And if you recall from what a dot product is, it's going to be, let's compute this one. It's going to be A00 times B00 plus A01 times B10. And this scales up to any size square matrix too. So, how would we realize this in code? If you wanted the super duper basic, easy enough to understand square matrix multiplication, how do you turn this into computer code? Pause the video and think about it. Well, let's just go into C++. Let's go into C++ and program it for ourselves. So, I'm going to define a matrix as being, let's just use a vector. Let's call this matrix 1. And then I'm going to make a second matrix, we'll call it matrix 2. Alright, now we just want, for our purposes, let's just make these matrices simple. So new line. What I'm trying to do is get this to be formatted as a matrix, a vector of vectors, and each vector is a, hold on. Okay, figured it out. So we can define our first matrix to be this. Then we can define our second matrix to be, I'm just gonna use random-ish numbers as our values. But we could have any numbers that we want. This is just the baseline for what we're gonna do next. Oh yeah, the error that I was encountering was, well, I forgot how C++ vectors work. It's curly brackets, not square brackets. So, if you recall from this picture here, this is gonna be our first row vector, and this is our second row vector. Then we have this, and then we have this as our column vector, and then this one as our column vector. For our purposes, let's define a third vector, and that's our product. Let's just define it to be 0, 0, and then 0, 0. Okay, so now what? Let's think about this. For each row in the first, for each row of matrix A, and then for each row of for each column of matrix B, we compute these entries, which is going to be our product. So this is matrix C, so this is C0, so this is going to be the element that corresponds to here. I hope this is making sense, by the way. Maybe I should also zoom in. So let's just write this out in code. I'll tell you for sure that we need a triply nested for loop. Okay. In this innermost for loop, we have product. Okay, so we'll have our product I, j equals. Actually, no, plus equals, because we're going to increment a value that we've initially set to 0. But if we had to return this as a matrix, we may have to create a 0 matrix first to store the result, if this is all making sense. So we're gonna take element I k times matrix 2 k j. Okay, so what is this saying? Well, let's look at this thing again. We're going to iterate through the rows of the matrix, of the first matrix. For each row, we're going to iterate through the columns of the second matrix. And then we're going to iterate through the individual elements of both vectors. We're going to multiply them, and then we're going to add the result to the corresponding element here. And that's just for the first element. So the first for loop iterates through the rows. The second for loop iterates through the columns. The third for loop iterates through the individual elements. So matrix 1 is going to be corresponding to A00. Yeah. Okay, actually, no, wait, go back. In our example, we're gonna, if we're in the first, yeah. Hopefully this all makes sense. It's one of those things, this is one of those things that you might be tasked to do, even though the math might not be fully grasped. Even I struggle with this sometimes. So it's good to sit down and just try to walk through the code. Try to understand what's going on. So yeah, in fact, let's just comment this. Let's just add comments to this. Iterate through each row of the first matrix, iterate through each column of the second matrix, iterate through the and then finally iterate through the individual elements of each matrix. Good? Okay, so suppose we had to compute that first dot product. So we would look at the first row of the first matrix and the first row of the second matrix. This element is 0, 0. This element is, well, also 0, 0. But this element is 0, 1, and this element is 1, 0. If we compute that by hand, we're going to get this result. 2 times 9 plus 1 times 2. We should get 20 out of that. So unless I did my math wrong or I did the coding wrong, this should result in the number 20. So let's add another matrix. No, let's add a function that will print a matrix. So I'll just put it up here. This is just a rough rough coding right now. So void copy this data type here. And then I'll just define the whole thing up here. Yes, less than. Print each row and then print each element in that row. So for int j equals 0, j is less than m square bracket j dot size j plus plus. And then standard C out M I J space. Actually, no. Tab. And then we can just end the line like that. Okay, now I can just copy this whole function here. Paste it here. Copy that. Replace it with matrix 1. Copy that. Matrix 2. And I want to print the result also. So copy that. Oh, it works. Wish me luck. Vector subscript out of range. Okay, it didn't work. Give me a bit. Found the bug. This should be MI, not MJ. Okay, so with that, we can run the whole thing. And just like that, we can do matrix multiplication. Big deal. So it's just a small matrix being multiplied by a small matrix. Not too impressive, though there are applications, machine learning specifically, or you might have to do, well, I say machine learning when I really mean more like neural networks. Those are, there's a lot of math involved with neural networks. Among other things, you have linear algebra and multivariate calculus. The part where you had to do matrix multiplication can be streamlined using parallel programming. So we don't have to calculate each individual element one after the other. We can calculate all of them all at once. So again, this is just a basic example with the 2x2 matrices. What if I wanted to scale up? For the sake of demonstration, what if I wanted to scale up to something larger? Then I'm going to need to expand these arrays. I'll be right back. Well, that took a while. So, basically I had it so that I have a bunch of I basically fill these with random numbers manually. So that was painful. Okay, so let's try to find the product of these two matrices. Will it work? Let's try it. Oh yeah, it didn't work because I never modified the for loop. So ideally what we want is, we want to have these three values. We don't want to hard code them, it's basically what I'm trying to say. So if this was an actual function in an actual program, we would not want to have it be dependent on, you wouldn't want to lock it into one specific size of matrix. Let's try again. Right, so now I have two 10 by 10 matrices, and we have a result here. Yeah, this should look about right, because I have a number that is no greater than 9 being multiplied by a number that's also no greater than 9. And I have 10 of them. So, by super duper rough estimates, I should have a number that should be no larger than 900-ish. Okay, so this should look about right. One other thing we can try for ourselves is an identity matrix is just a matrix that's all zeros except for a specific diagonal of ones. Therefore, we can use this to do something special. Any matrix multiplied by an identity matrix will return the same matrix as before. Build errors. What broke? Oh. Matrix 2. Try again. 214748367. Identity matrix and 2147 yada yada yada. And then 9712. Yep, we got the same matrix out. Okay, so again, basic example of matrix multiplication. How would we make this parallel? Well, remember the example where I had dot products? One thing I said that we should do is we parallelize the innermost for loop. We can do that too here. Let's try it out. I'm going to put in Pragma OMP parallel 4, and since this is going to be a critical section, I'm going to add Pragma OMP critical, because only one thread should be doing this operation at a time. If we want to be absolutely sure that it's one thread accessing this operation at a time, what I could do is enclose this in parentheses, curly brackets, copy this, paste it back here, declare a variable called increment, copy paste, and then I can just copy this here, and then I'll just print f what this thread is calculating. This is just to show that this is really being multi-threaded, so ready. Right, so here's our parallel for loop, and here's our critical section. One thread at a time can only execute this code. And because we have it so that we're multiplying by an identity matrix, we have a whole bunch of multiply by zeros. We also have a lot, and I mean a lot, of we have a lot of multiply by zeros, but we also have here a whole bunch of threads. Yeah, we have a bunch of threads doing their own calculations. So here's the thing. Because there's only 10 loop iterations each, we only needed OpenMP decided we only needed to go up to 10 threads. So this works too. So yeah. You see, the real test is ensuring that what we're doing here is not only, well, actually there are two considerations, and ultimately what we're going to do is figure out whether any of this is making the program any faster. But you could say another consideration worth keeping note is, are we doing this in a way that is thread safe? I'm going to talk about a little bit more about thread safety possibly next week. So, that's something we'll talk about more later on. Thread safety. Why is the Pragma OMP parallel for the last for loop? What happens if we put it in what happens if we make a different for loop parallel? And of course, what else can we do? We've just gone through a few basic examples of making certain operations parallelized. But this turns out to be one of several ways of achieving parallelism. Sometime next week, I'm going to assign a short answer question. So be prepared for that as well. It's going to be we're gonna talk through the question in class, of course. Right now, your first homework is to, well, try out OpenMP for yourself. So with that, I'm going to end the video. It's a little bit short. Again, try out OpenMP for yourself. Reach out to me via email if you have any questions, or Canvas messages. That works too. We'll come back on Monday to address any questions that we may have with debugging. We're also gonna bring up the first short answer question then as well. We'll look at more into matrix multiplication and thread safety. All in the video here. Yeah. That's going to be it for the video, and I guess that's going to be it for the video. I'll see you next week in class.